Hi, everyone. We have lecture 20, and the main topic today is the start of the discussion on transistors. And there are two main types of transistors that we are going to talk about this term: the bipolar junction transistor and the field effect transistor. And we are going to start with the first one. But before doing that, there's a couple of things I wanted to mention. Well, one thing I wanted to mention, and that's the fact that we spent a week talking about op amps, and I realize this is toward the end of the term and things are building up. And if you feel that you're not up to speed on op amps, don't let that get in the way of learning about transistors. The discussion we have here does not hinge on a very strong basis on op amps. We are not going to make too many direct connections to op amps, at least not at the beginning. Okay? So even if you don't know op amps, you should be able to follow this. There are high-level connections, and we will discuss those later on. But right now, these are really new devices that we're going to talk about. And so if you feel like you couldn't catch up with things last week, don't let that get in the way of following this. So that's one note I wanted to make. But before starting the formal discussion on transistors, I wanted to do an example with a diode circuit to remind us of the kind of thing that we talked about a couple of weeks ago, because there are some connections between diodes and transistors. So for now, we'll set this aside and do a little review / warm-up example. Okay? So for now, nothing about the transistor. Consider this circuit. And imagine we ground this for now. So we have a diode here and a current source. Now, that's a controlled current source, a dependent current source. And it's a current-controlled current source in that it's current. So let's call this one VD and ID. So that's a diode there. And the current in this branch is controlled, imagine, by the diode current by a factor of alpha. So that's a current-controlled current source. Let's call this R. Okay, so the voltage at this node is basically VD, if that's how I'm choosing to call things. And this voltage up here, let's call it some V naught. Okay, that's a node up there. You can imagine I have connected a voltage source there that applies a voltage V naught. So this is a little circuit that I've built. And this diode is, imagine it's not an ideal diode, but it's a more or less real diode. So it has an IV characteristics curve that's like this. Remember that there was this forward region where you had this exponential dependence, right? Where the current ID was approximately proportional to the exponential of VD over VT, VT being some thermal voltage at room temperature about 26 millivolts. Okay, so I'll maybe write that down. So approximately saturation current exponential of VD over VT, this being thermal voltage. Okay, nothing new there. And back when we were talking about this, we said there is also an ideality factor there. So n VT, and that n could be 1 or something between 1 and 2 typically. And also this was exponential. There was this exponential minus 1. But if this exponential term starts to grow, that 1 next to it can be neglected. So that's why I'm putting approximate here. But this is kind of the essence of the behavior of a diode in the forward region, right? So that's that exponential behavior. The current is an exponential function of the voltage applied across the diode. So what I'd like for you guys to do is to take a few minutes and try to understand this circuit that I've drawn there, analyze it, and let's call this node voltage here. Let's call this V1. Okay? So consider this. This is VD, and that's V1. And here's the exercise I want you to do. Qualitatively plot the transfer characteristics from the input to the output of that circuit, namely V1 as a function of VD. So you want a plot on axes like this. V1 as a function of VD. Okay, so try this on your own a little bit. I'm just trying to do a reminder of diodes, looking at one particular diode example. All you're trying to do is to consider different values of VD on this axis. Could be some negative values, some value around 0, a little higher, a little more positive. And for each such value, think about what V1 would be. And then plot a number of dots and then join the dots. That would be your V1 versus VD. Spend another minute or two on it. Well, let's try to analyze this together. So first of all, let's start with some value on the negative side. So imagine VD is a relatively sizable negative value. And the diode that I have drawn here, for now I have not gotten into the breakdown mode. Assume that this reverse saturation goes on the way I've drawn it. And obviously I've exaggerated it there, right? Because you know that in practice this is a very small current. This is the reverse saturation. It's a very small current. And goes for a long time until you reach that breakdown. But for now, let's neglect breakdown. Imagine you can apply a very large negative voltage to this diode, and it still has that negligible saturation current. Now, again, remember that this was, in reality, it was more like this, but I said approximately. You can neglect that -1. It doesn't matter. It won't make a substantial change to this analysis. So if VD is a negative value, somewhere here, the diode current is going to be what? Almost 0, right? An extremely small reverse saturation current. So more or less 0. If the diode current is 0, then what is alpha times the diode current? This alpha being some finite number. Well, that's 0. So what is V1? Not 0. V0, right? Because there is no current going down, so there is no voltage drop on R. And so V1 is V0. And that holds for essentially any negative value of VD. And again, we have neglected breakdown. Okay, so if VD is negative, V1 is almost V0. Let's call this V0. Okay, because there is no current going through that resistor, there is no voltage drop. Things start to get interesting when VD is a positive value. Now, if VD is 0, the diode current is 0. And again, alpha times ID is 0, and V1 is the same as V0. As you increase VD further, so imagine you reach VD equal 0.2, 0.3, 0.4 volts. Not much happens because the diode initially has a slow increase in its current, right? By the time you reach about 0.6, 0.7 volts, the diode current starts becoming substantial, right? This is what we've seen with diodes, nothing new. So it's really when VD gets around 0.6, 0.7 that there is a substantial diode current, and as a consequence, a substantial alpha times ID. That's just a current-controlled current source that multiplies that current. And if that current is substantial, then there is a substantial voltage drop across that resistor, right? And so V1 starts to descend from its value V0. So it's really this current here that is making the difference. And that's just alpha ID, right? Because V1 is just a node there for whom we are measuring the voltage, but the current going through R is the same as alpha ID. So what we are saying is that it's when VD starts approaching 0.6, 0.7 that things get exciting. So by the time VD is around 0.7 or slightly higher, you might say that diode is fully on. So let's say if this is 0.7, that diode is fully on, and you have a substantial current, and the output has gone down significantly and reached a value that is V1 minus alpha ID, right? So by the time, let's say this is around 0.7, that output has become, has gone down substantially. Output has reached a substantial drop compared to V0. So it's V0 minus alpha ID. ID corresponding to 0.7 volts of voltage input. And it's substantially lower than the original V0. And that's a kind of smooth transition because as you increase VD from 0, well, at 0.1, 0.2, 0.3, and so on, there is a gradual increase in the diode current and consequently a gradual decrease in the output voltage. And eventually, what happens? Does this keep going down? Or up to what point does it go down? Let's imagine I keep increasing VD. So I go from 0.7 to 0.8, 0.9, 1.5 volts, 2 volts, 10 volts, 100 volts. What happens? What happens if VD is 100 volts? That's a trick question. You should not go as high as that, right? So don't go much beyond 0.7. But hypothetically, you know, in an ideal world, this diode could take any voltage, right? Even 100,000 volts. The current would be enormous. Calculate the exponential of 100,000 divided by 0.026. And you will have a problem getting the number from a calculator. But so in practice, of course, you're not going to go beyond 0.7 or 0.8. But in theory, yeah, this curve would keep descending. But and in fact, I think it would keep descending faster and faster. But let's limit ourselves there so that we don't damage things. Okay, this is where interesting things are happening. Yes. Yeah, very good question. One thing here that, and this is something that could be very confusing. One thing I have not shown here is a voltage source that's driving this. I meant to imply this. Now, I did not intend to have a load at the output. So this I don't have. But the voltage source I do have so that I have a closed circuit. That I meant to imply. But very good point. To be clear, let's draw that there. Okay? Otherwise, then, as you said, alpha should be 1 because KCL would require that. But what I'd like for us to do now is to focus on that region that I have circled in blue. What's happening there? Now, what's happening is this. As the input voltage is changing somewhere around 0.7 volts, you see, for little variations in the input voltage, I think you would agree that there is a substantial variation in the output voltage. Now, how do I know that's really substantial? So let's put things into perspective. I'm sorry, I forgot to include the resistor here. This is V1, was V0 all the way. And then if this was around 0.7 volts, at this point, it was V0 minus R times that alpha ID. And that's the ID at 0.7 volts of input. Okay? Now, you notice if this quantity, R alpha ID, is a substantial number, then this is a substantial drop from V0, right? Now, ID at around 0.7 would be a reasonably large value. That's a diode that's on. So I'm talking about R times alpha being a reasonably large value also. And so then I have a pretty nice drop like this. Okay? This is very interesting because what it's saying is that for a small range of variations of the input voltage, if I'm somewhere here, the output is changing, let's say, from this point to this point. So for a small range of variations on the input, I have a pretty large range of variations on the output. This is what you can accomplish with a diode circuit. Okay? So I'll summarize this, assuming that R alpha is a reasonably large value when the input changes by a small amount around 0.7 volts. That's when you transition from the diode being almost off to almost on. The output of the circuit, which is in this case V1, changes by a large amount. Okay? By the way, pay special attention to what's happening on that current-controlled current source. Because on one side, its lower node is at voltage VD, right? If you look at the variations of VD in the range we are interested in, that's a small variation, somewhere around 0.6, 0.7 volts. On the other hand, V1, which is the top side of that current supply, current source, is varying greatly. So the voltage difference across that current-controlled current source is changing greatly in that range. Is that a problem? We have a current-controlled current source. The voltage difference across it is V1 minus VD. And in this range, in this blue range, V1 minus VD is changing greatly. Is that a problem? If you're silent, you're happy. It's not a problem. It's not a problem. It's a current source. A current source, an ideal current source, should be able to accommodate any voltage difference across it, right? An ideal current source. Of course, such a thing doesn't exist, but on paper, that's fine. All right? Now, again, notice that I have not ventured to go much beyond VD because that diode will not be happy. It's not a good thing, even on paper, to apply a 10-volt voltage across a diode. Okay? It's just not a nice thing to get used to. All right? Okay, so I just wanted to do an example with diodes and resistors, and in this case, a real, more or less real diode with its exponential characteristic, to see how it behaves in a resistive circuit. And see that you can get an interesting function whereby if you're changing the input by a small amount in the circuit, the input voltage changing by a small amount, around 0.7, the output voltage is changing by a large amount, if R times alpha is a large number. Those are parameters of your problem. Okay? Anything we should discuss a little more? Yeah, ID of, ID of 0.7 volts. Yeah. So if this point is 0.7 volts, that's all right. Let's take a 10-second pause and. Now I want to start the new topic, the bipolar junction transistor. Show of hands, how many people have seen BJTs before? Only 4 or 5 people? You all have. This is a BJT. What we've been doing for the last half an hour or so is a BJT operation. Okay? So that's it. We can conclude the lecture for today. This is one aspect of operation, but this is something that I feel captures the basics of BJT operation from several points of view. And in fact, it's also closely related to the actual physics of operation of a BJT. But what you just saw here is called, it's essentially a BJT-based amplifier circuit. You see, if you had chosen R alpha, the parameters such that R times alpha was a reasonably large value, then with a small change around the input voltage, around 0.7, you would get a large change in the output voltage. So you are amplifying the variations of the input voltage at the output. And this is, in fact, a circuit that you would call a common emitter amplifier. And we will see that more formally. But this is a picture that does not capture everything that a bipolar junction transistor does and all its limitations. This is a simplified picture. But it's a picture that captures a very, very important chunk of the behavior of the BJT. And in fact, the chunk of the behavior that we are most commonly interested in. Okay? So if you understand this circuit, you already understand a good deal of the operation of the BJT and its use in circuits. Okay? So this is an example that I'd like for you guys to go home and do again on your own. You can even do it more accurately, numerically, using a computer. Plotting this and actually calculating ID as a function of VD and plotting this for various values of alpha and R and getting the exact curve. It would be a nice exercise to do. It would be very insightful. But I hope this also, to some degree, breaks down the barrier to entry for transistors, because the transistor is an element that instead of two nodes has 3 nodes. So unlike the resistor or diode or capacitor or inductor that have 2 sides, this has 3 sides. But I hope this example again helps us get over that apparent difficulty, because this is where your transistor is, essentially. This is inside the circle is your transistor. So you see there are 3 nodes coming out of it. One down here that I have connected to ground, another one on the left that I've connected to VD, another one on the top, at the top there that I have taken my output from. Okay? It's a 3-pin element. And it behaves very much in this manner. Now, does anyone know what alpha is for a transistor? What the value of alpha is? It depends on the transistor, of course, but more or less. Or what is, for a desirable transistor, what is the value of alpha? It's about 1. Now, that might sound very boring, because you're starting to think, well, what is this? I have a diode here. Then I have a current source up there with a multiplication factor of 1. So it's the same current as the current of the diode, more or less. So what's the big deal? Well, the big deal you have to judge by the outcome. And that's all the technologies we've developed for the past half a century. So it is a big deal. It all hinges on this. And a very big part of why is this amplification function that you just saw. That for little variations in the input within a given range, the output can vary a whole lot. And that's of enormous consequence in terms of things that you can do with it. Okay? So with that, I'll define the bipolar junction transistor a little more formally. Like in the case of the diode, we will start by describing it at the circuit level. We will not get into the physics now. Toward the end, based on how much time we have, we'll hopefully briefly discuss the physics of these a little bit. But again, similar to the diode, the physics depends on, we have to build it up from quantum mechanics and solid state physics. So for now, just think about a circuit level abstraction. And also accept from me that there are two types of bipolar junction transistors, what you call an NPN transistor and the other one a PNP transistor. And that has to do with the structure in terms of the semiconductor materials or the impurities you put in the semiconductors and the way you form these junctions. But its structure is something that has three sections. And the diode had two sections. There was one junction. The transistor has three sections or two junctions. And at a circuit level point of view, it's represented like this. So it's three nodes. This is called base. This is called emitter. And this is called collector. This is an NPN transistor. And we will, once we understand things with this, we will be able to readily apply all that knowledge to PNP transistors also. But for now, let's stick with what we call an NPN transistor. Now, how do we describe the behavior of this transistor? This little arrow that you see here, going from base to emitter, is essentially trying to indicate the same behavior as a diode. It's suggesting that there is a little diode there. So you have a base emitter connection where you essentially have a diode. Then you have a base current. You have an emitter current. And you have a collector current. The behavior of the transistor is like this. Between base and emitter, you have a diode. There's a current going through the emitter that has an exponential dependence on that base emitter voltage. And the collector current is just a multiple of that with a factor alpha. And that alpha is very close to 1. So in terms of the behavior, you could think of it like this. IE is approximately some saturation current. Let's say emitter saturation current, exponential of VBE over that thermal voltage. And again, I neglected -1. Okay. And IC is simply alpha times IE, where alpha is approximately equal to 1. It's like 0.99, 0.98. So approximately equal to 1. So this is it. Now this is true as long as this alpha being almost 1 is true, as long as you respect some constraints. And that is when the collector voltage doesn't drop too far below the base voltage. Okay? So imagine if you have grounded your emitter, like we had done here, and you apply the base voltage of about 0.7, that alpha is approximately equal to 1. As long as your collector voltage, V1, is not dropping far below 0.7 volts. Okay, if it goes to 0.6, it's okay. 0.5, it's okay. 0.4, 0.3, it's starting to not become okay. Okay, so we'll say as long as the collector voltage doesn't drop too far below the base voltage. If you wanted to quantify it, as long as VC is greater than, or let's put it this way, maybe easier. VC minus VB is greater than, let's say, 0.4 volts. And this is, again, approximately. Okay, none of these is an exact point. 0.4, 0.3, 0.5, depending on the application, the transistor. Okay, so basically I have called this VB. This is a node voltage, VC, and VE. Okay. With this knowledge, you should already be able to solve a wide variety of transistor circuits. And of course, there is a little more detail that we'll not now talk about. But you have already seen that such an element could do this. So replace the circle with a transistor, and you get that amplifier. Anything you guys would like to emphasize a little more here? I'm deliberately trying to go relatively slowly here because I want these to really sink in. So what is really happening here? What is it that makes this so valuable? If you say, well, all I've done here is taken a current in the emitter line and essentially duplicated it in the collector line. That may not sound very exciting. But what is important to keep in mind is the fact that the emitter current itself is the current of a diode. And the current of a diode can rise with the applied voltage to the diode very, very steeply because it's an exponential function. So what this device is doing is taking a voltage input between the base and emitter, giving a current at the emitter, but then essentially duplicated at the collector, which is an exponential function of that voltage difference. So it's giving you a current at the output that's an exponential function of the voltage at the input. You see, it's taking a voltage at the input, giving you a current at the output, at the collector, that's an exponential function of that voltage at the input. And that's the essence of amplification. And that is why you were able to do this here. The reason we got a wide variation in the output voltage with little variation in the input voltage, is that the output current essentially rose exponentially with the input voltage around this region that I have highlighted in blue. Yes? The output current is not negative here. Why do you say it's negative? Let's look at these currents. What's happening here? What does KCL say for this device? If you consider the fact that charge is supposed to not be accumulated in here, the sum of currents going in should equal whatever comes out, right? So if you apply KCL, you have IC and IB going in and IE leaving, right? So IC plus IB minus IE equals 0. Okay? Or written another way, IC plus IB is equal to IE. Now, I said that alpha is more or less equal to 1. And to be more precise, slightly less than 1. It's not more than 1. It's less than 1. Let's say 0.99. Okay? Now, you can write things in that way. This IC is alpha IE. Now, IE, the way we have indicated it, is a positive value because there is this small saturation current of that diode times the exponential of a large number. That's a large positive value. IE is a large positive value. Alpha times IE is almost the same as IE, and it's a large positive value. So the collector current is in the direction that we have indicated, and it's a positive value. And so is IB. And from here, you can work things out. IB is IE minus IC, which is IE minus alpha IE. So you can write it like this, 1 minus alpha times IE. Equivalently, you can also write it like this. You can write it as, instead of replacing IC with alpha times IE, you can write it like this. Replace IE with IC over alpha. And this thing, give it another name. Is this beta a large number or a small number? How much is beta? If my alpha is 99%, how much is beta? Close to 100. And that's typical for a transistor. This might be the single most important equation of the BJT transistor. The collector current, roughly 100 times the emitter current. I think this is a good time for a break, because now we are going to start talking about more specific examples. All right, should we start? Look, again, I want to emphasize the importance of this example, because, you know, as much as it might seem like a simple circuit, this is very important for a large chunk of the operation of the BJT, but actually also very important for a good chunk of the operation of the field effect transistor, which we are going to see later. Now, there are important differences between the two transistors. But conceptually, in terms of this kind of amplification behavior, there are a lot of similarities. So this is a very important example, and that's why I'm trying to spend more time on this, just having you guys stare at it for longer. And going from that to here, okay? So let's remember also that if alpha is very close to 1, beta is a large number. For a good typical BJT, beta is of order 100. Now let's get a little more technical and define the current voltage characteristics of the transistor a little more formally. This is what we've been doing with every element that we've done so far, right? We've looked at the current voltage characteristics. And that's what we're going to do with the transistor. Consider this. Again, same thing that we had before. Emitter, base, collector. By the way, as an aside, we call this thing an emitter. Can anyone guess what it's emitting? Current is a good start. More specifically, electrons. Exactly. It's emitting electrons. Has anyone heard of vacuum tubes? Yeah? Some of you might still prefer vacuum tube amplifiers. Well, in those, well, how about the cathode ray tube that the old television was based on before we had flat panel displays? In that cathode ray tube, there was a filament, a tungsten filament, very much similar to what you have in an incandescent light bulb. That tungsten filament, you heated it up to 2,000 degrees, and guess what? It emits not only light, but also electrons. And then you had, at a gap some distance away from it, in vacuum, you had another electrode which collected those electrons, hence the name collector. And then you had some gate in the middle that could deflect the electrons one way or the other and prevent them, for instance, from reaching the collector, or modulate the number of the electrons that reach the collector per unit time. So there is a lot of similarities. And in fact, if you want to understand these devices well, I personally think you should start with vacuum devices. And we'll see if we have time to discuss that later on. But so the name emitter and collector and base, these are very meaningful. If I ground my emitter and I apply a voltage between base and emitter, let's call this VBE. And if I apply a voltage between the collector and the base also, let's call this VCB. What I'm interested in particularly is the behavior of the collector current as well as the other currents. They have a lot of connection. Particularly interesting is the behavior of the collector current as a function of these two voltages. And because we have three nodes for this device, one voltage is not sufficient to describe it fully. We have to have two voltages. Do I need a third voltage, by the way, VCE? Do I need a third voltage source there? No, because VCE is simply VCB plus VBE, right? This is just KVL. And IC plus IB, maybe let's write it the other way around. IE is simply IC plus IB. This is KCL. So these are things that you know in this device. This is what the characteristics look like. let's first look at IC as a function of VBE. IC as a function of VBE. What does that look like? The current in the collector as a function of the voltage applied between base and emitter. Let's scroll up. It's that. This alpha ID, which is alpha times this curve. It's that exponential. Okay. So IC as a function of VBE is approximately some saturation current. Let's call this saturation for collector, exponential of VBE over VT. Now you might say, wait a second, I just said I needed two voltages, VBE and VCE, to describe this device fully. Yet here I have said IC is simply an exponential function of VBE. So what happened to VCB? Does that matter? Well, let's think about it this way. Let's go back to this example here. The current ID depended exponentially on the voltage VD, and the current in the upper branch was simply alpha times that. Did this current alpha ID depend on the voltage at V1? No. In this simplified model, it didn't. And in fact, ideally, you wish you had a transistor where this was the case, and the variations of the collector voltage did not affect the current. That would be good for many things. In reality, that's not the case. Like I said here, this was the condition. As long as VCB, this should have a negative sign here. As long as the collector voltage is not too far below the base voltage. It's okay if it's about 0.4 volts below the base voltage. Okay? So I'm saying equivalently VC should be VB greater than VB minus 0.4 volts. It can go about 0.4 volts below, and still things would work. So this is the case. You have this nice behavior if VCB is not too far below minus 0.4 volts. If VCB is very, very large, if it's 200 volts, that's fine. Of course, at some point the device might break down, but let's set that aside. In principle, if VCB is a large positive voltage, it doesn't hinder this basic operation. So to see that maybe in another way is, let me write down here. This behavior here is as long as we are within the desired mode of operation. And I'll specify that a little more. Or let me maybe be a little more careful. Let's not write this here because this could lead to confusions later. Let's draw another curve. There, hopefully, things will be a little clearer. And that's when I plot IC, so the same current, as a function of VCE. So this VCE is the collector emitter voltage. It's the sum of those two, right? VCE, as we have it up there, is VCB plus VBE. So let me just write it here. this is a very important curve, so please look very closely. Imagine you have a transistor where you have applied a VBE of about 0.7 volts at the input. So you have turned on that diode. Okay? So your VBE is somewhere around 0.7 volts. Now you start increasing VCB so that the sum of the two, which is your VC, is a large voltage. It's maybe 2, 3, 5, 10, 20 volts. Okay? So I'm somewhere here on the axis, large values. What would you expect the behavior of IC should be as a function of VCE? As I keep changing VCE by keeping VBE constant and increasing VCB, how should IC change? Think about that for a minute. And again, have this picture in the back of your mind. If I have kept the voltage across this diode constant, but I'm increasing the voltage at the output. So suppose I didn't have R, I had just directly connected this to some voltage source, and I was increasing that. How did you expect the output current to change? On this circuit, how does the output current change? If I imagine you don't have this, and you have directly connected this to some voltage source. And if I keep changing V1, how should the output current change, this alpha ID? It should not change. It's dictated directly by the current here, which is dictated by the voltage VD at the input. That's essentially what you want. That's the desired outcome. And in a good transistor, you will get that for a wide range of VCE. So the dependence of IC on VCE is, again, you might say something pretty boring, constant current for any voltage. Is that a boring device? Constant current for any voltage? How would you call that? It's a current source. You see, it's a current source controlled by not its own voltage drop, but the voltage drop somewhere else. You see, the value of IC is determined by the voltage across the base emitter junction, not by the voltage across the collector base junction. And that's what you want. It's a current source controlled by something else somewhere else. Okay? This would have been ideal, but in reality, things are not ideal. And as I said, this condition of having an alpha of equal to 1 and a large beta and things working nicely like this is applicable as long as your VCB stays more than a little than, let's say, minus 0.4. Okay? So now imagine if this is approximately 0.7 volts, and this is greater than approximately minus 0.4 volts. The sum VCE is approximately greater than 0.3 volts or so. Now again, none of these are numbers set in stone. Okay, it's just the order of magnitude. What happens is if you go down like this to lower and lower voltages, so let's say this is approximately 0.3 volts. If you go below that, the collector current will drop. And it will not have that nice behavior anymore. This is where you want to operate things. This is called the active mode. This is called the saturation region. Now you might say it looks a little weird because you might prefer to call the part that's straight line saturation, but this is called saturation. So this is the saturation region. The active region is very often the desired mode. What I meant by the desired mode before, which I erased, is this active mode or active region. Now, question for you guys. In the active region, you see I have a constant IC. Does that mean that I have a constant current source that I cannot change? How would I change IC? By changing VBE. So in fact, to be a little more complete, you would draw a number of curves that look like this. Each of these curves correspond to a different value of VBE. Let's call this VBE1 for VBE2 and VBE3. And in this particular case, the order is like this. VBE3 is greater than VBE2, and that's greater than VBE1. They're all around 0.7, but maybe one is 0.65, the other one is 0.68, the other one is 0.72. And a small increase in VBE will correspondingly lead to a large increase in IC. But what the second graph is saying is that for a wide range of VCE, there's no change in IC. So IC is solely determined by VBE. And that's the beauty of this device. It is a voltage-controlled current source, regardless of, as long as you are within the active region, what the voltage drop across itself is between the collector and base, or collector and emitter. And this is what allows you to do all these wonderful things. You have this little input that you can change, tune that the input to that diode, and the output voltage can swing wildly because you can change the output current by using the changes in this input voltage, regardless of the output voltage itself. So this is really the key to understanding the behavior of this device. Of course, if you had an ideal current source like what we have up here, things are always in active mode, if you want. Regardless of, even if your V1 is minus 200, right, this would still be in active mode. But in reality here, if your collector voltage drops to a fraction of a volt below the base voltage, the collector current will drop.
Need so many transistors?
Why do our devices need so many transistors? So let's say in your computer, right? Let's look at what this transistor here is doing. The first example. Okay, that's a very good question. I have a device where I can, by using some changes to the input voltage, create a significant change in the output voltage, right? So imagine I have, if I think of the input voltage here as a bit of information, 0 or 1, depending on the amount of voltage. So let's say 0.5 volts is 0, and 1 volt or 0.75 volts is 1, right? If your input is 0, your output is 1. If your input is 1, your output is 0, right? You have changed. This is essentially how transistors operate in your logic circuits. Okay, and so if you want to make, so that's basically a not function that I just described, right? By changing the input from 0 to 1, you're changing the output from 1 to 0, binary. Similarly, you can implement other functions. And so typically, to implement a logic gate, you would have a number of transistors, right? Now, if you have a processor with a large number of logic gates, you have that many transistors. Yeah. Now, this is just the logic, the computing application. But think about the amplification application itself that we looked at initially. That's more of an analog example. You're amplifying a signal. If the input, imagine at the input you have a signal. Again, you're picking up from a small antenna of a mobile device. And the variations of this signal, based on what you're picking up from the air, from the base station, the variations are a few millivolts, around 0.7 volts. Well, those would lead to large variations at the output, which now you can connect to a speaker and actually hear things, right? You know, I think the old transistor radios, you guys probably have heard there used to be this thing called a transistor radio. And of course, now all radios, you might say, are transistor radios. But I think some people used to call the transistor radio the transistor. I think that had become a, I think I heard or read somewhere that, you know, the word transistor was also used to describe the transistor radio, because that's how you amplified the circuit, the signal in the radio. And this was after, so after transistors were invented in this form, and you didn't need the vacuum tubes, and you didn't need to wait for them to warm up and so on. So radios became compact, and people could have them in their pocket. Anyway, so that's an amplification example. And then there is everything you can think of building up on that. By the way, how can I make a diode out of a transistor? Take this, just the transistor element itself, make a diode out of it. How would you do that? It has a diode inside, but you want to open it up and break the collector junction, and so that would be a little painful. Do something from the outside. Yeah, connect the base and the collector. This is a diode. If you do this, that's a diode. Because now you don't need this extra pin. So if you put this in a package and sell it, that's a diode. All right, so let's now, with these in mind, let's solve a more detailed and specific example. And what goes on exactly in the active versus saturation region, we'll come back to, okay? But I think we need to see a few examples to start getting a feel for this, and then discuss them more in context. You might also be wondering what would happen if, for instance, I applied a reverse bias. So those are things we can look at as we go along. One final thing I'd like to mention briefly before we look at examples is this. You know, I've been saying how the base emitter junction or part is a diode, as indicated by that arrow. Actually, the collector base portion is also a diode, because the structure of the device looks like this. You have, this is the physical structure. You have a semiconductor, N-type semiconductor, a P-type semiconductor, and another N-type. This is the base emitter portion. You might say this is a diode. And this is the collector base portion. That's also another diode. And in fact, in the active mode, your base emitter diode is forward biased, and the collector base diode is reverse biased. Again, to appreciate how this works and how you can have that that large collector current, if that diode is reverse biased, we would have to get into a little bit of physics of operation for this device. And hopefully we'll have time to do that later on. But this is two back-to-back diodes, you might say. But it would be incorrect to think of them as two separate diodes attached externally. There are two back-to-back diodes that are very closely integrated. And in particular, this middle segment is actually a thin layer, relatively thin. Okay? But anyway, so this is something hopefully we'll have time for later on. For now, at the circuit level, let's study this problem. For this circuit, find V out as a function of V in. Let's call it V in for consistency. So I'm looking for a graph like this. V out is the voltage at that node with reference to ground. V in is the voltage I've applied here. Well, let's take a look. It's very much like the example we started the lecture with today. Here I have the base current, the emitter current, the collector current. And I haven't connected the output node to anything else. So I also have the collector current going through here. Okay? If V in is a very negative value, the base emitter diode is biased negatively. It's in reverse bias. There is essentially no current. And so the collector current is 0. I'll write it here. If V in is less than around 0.7 volts, say, IC is small. And recall that the output voltage, which is VCC minus RIC, is approximately equal to VCC. It's only when V in starts reaching around 0.6, 0.7 that things become exciting. So V out is simply like this at VCC until V in hits somewhere around 0.7 volts. By which point we have some drop on the output. Now, how long will this keep going on? If I keep increasing VBE, can this keep going on forever? Well, now we're dealing with an actual transistor, right? No. Where will things start to go wrong? Where is the point at which you start hitting a region where you keep increasing the input voltage, but the output current doesn't change much anymore? Look at this behavior. Again, remember that if the collector emitter voltage becomes smaller than around 0.3 volts or so, then the collector current for a given VBE starts dropping. Now, of course, as you keep increasing VBE, you will go to progressively higher and higher curves. So the collector current wants to increase, but it won't increase as fast because, on the other hand, you're decreasing VCE. So not only you go to higher curves, but you're shifting to the left also. And the increase in the collector current is not going to be as high anymore. You see, the more I come closer to this end, if I'm around here, if I go from curve number 1, VBE1, to VBE2 to VBE3, I'm not gaining a whole lot of increase in the collector current, right? Whereas if I was here, I would get a significant increase in the collector current going from one curve to the other. All right? So as my VCE decreases, which is exactly what you have here, because as the output goes down, well, output is just VCE, right? The voltage between collector and emitter. You're reaching the saturation region where the collector current is not going up with VBE anymore, not significantly anyway. You're reaching a range where the collector current will not respond so sensitively to the input voltage anymore. And so the output will not keep going down anymore. And so the output will more or less saturate. And this is where your V out has reached somewhere around this 0.3 volts or a little below. So this is maybe, you might say that the onset is around 0.3 volts. Okay. Once the VCE once VCE, which is the same as V out, reaches around 0.3 volts and below, the increase in VBE does not lead to a significant increase in IC anymore. And that's why the output voltage doesn't change anymore, because the output voltage is simply VCC minus RIC. So V out, which is VCC minus RIC, does not change with V in a significant way anymore. Essentially, the behavior we saw at the beginning in this example, but it ends somewhere. It works only for the chunk of the operation of the transistor where the transistor is in the active mode and hasn't reached saturation. Now, I'd like to slightly augment this example and do this. Consider this circuit now. This is VCC. Call this collector resistance and emitter resistance. Apply your V in here again. And measure V out here. Now do the IV characteristics, the output versus input characteristics for this. how do things change? This is an example I'd like to ask for you guys to take a look at home, work on a little bit, and draw the characteristics. Now, qualitatively, you would expect that there is a behavior to a large degree similar to the previous circuit, because if you increase V in, that surely leads to an increase on the base emitter voltage. Now, the difference is the base emitter voltage is not equal to V in, right? V in now is the base emitter voltage plus the voltage drop across this RE. But nonetheless, with an increase in the input, you would increase the base emitter voltage. The increase in that voltage should then lead to an increase in the collector current, as we've been seeing all along. And an increase in the collector current should contribute to a decrease in the output voltage. Now, up to what point and at what rate is the question. So if you think there's going to be something kind of looking like this, again, similar to the previous example, go try to find out what this point is and what this slope is. Now, don't take it from me that it's going to look like this. Go think about it. So this is an example to work on at home, and we'll look at in detail next time.